Hello, my name is Ruba Kiani, and welcome to my individual software engineering project presentation. Today we're going to be exploring the topic of unit testing, one of the most essential practices in modern development in software. I'll walk you through what unit testing is, why it matters, tools we use, such as JUnit and Mockito, testing strategies like test-driven development, and the perspective of industry experts like Martin Fowler. We'll go over some common challenges and how unit testing fits into the broader landscape of software quality assurance. We'll also talk about real-world testing strategies and how you can use these practices to write a cleaner, more precise, more reliable code. Whether you're working on a small script or a large-scale application, testing plays a critical role. Before we jump into the details of unit testing, I want to set the stage of why this topic matters so much in software development world today. As developers, we don't just write the code. We solve problems, build systems, and deliver solutions that people depend on. Helps us in the future and in our workforce. But no matter how experienced we are, mistakes can happen. That's where testing comes in. Unit testing acts as a safety net. It lets us move quickly, experiment, and make changes without constantly fearing that we've broken something. It's a process of writing small, focused tests to validate that each part of our code does exactly what it is supposed to do. When done well, unit testing gives us a confidence that will improve our code, improves our code quality, and actually saves time in the long run. In this presentation, I'm not just going to show you how to write unit tests, but I want to help get a better understanding of what unit testing is. So let's continue. What is unit testing? Unit testing is a method where individual parts of code, called units, are tested independently to ensure they function correctly. A unit is usually a single method or function by testing each unit in isolation. Developers can catch bugs early, reduce maintenance costs, and build a foundation for reliable software. It's like checking each component of a machine before assembling the whole device. You want to ensure that every piece works properly on its own. By catching defects early, we reduce the cost of complexity of bug fixes. This is especially helpful when making changes or adding new features, since a good unit test will quickly alert us if we've broken anything. Unit testing is also encourages modular, loosely coded coupled. When writing code that can be easily tested, you're naturally drawn towards cleaner design principles. JUnit is the most powerful framework for unit testing in Java. It also allows developers to write automated tests and give feedbacks instantly. Mike Van Putten explains how JUnit makes it easy to create a structured test case using annotations like @test, @before each, and @after each, but we'll explain in later slides. This framework is fast, flexible, and essential for writing professional production-ready Java code. When you save or compile your code, the test can run automatically, showing you whether your changes have broken anything. JUnit also works seamlessly with CI or CD tools like Jenkins Enterprise Application. Its powerful assertion and lifecycle management tools allow for detailed high-quality testing with minimal setup. So, why use JUnit? Main unit testing framework helps reduce the risk of breaking existing code, or it can encourage clean, testable designs. So more about unit testing. Besides JUnit, we have other tools like Mockito for mocking, PyTest for Python, and Jest for JavaScript. The benefits of unit testing include faster debugging, reduced code complexity, safer refactoring, and better documentation. However, unit testing is not a silver bullet. It should be used alongside with the system and acceptance tests. A balanced testing strategy ensures that software is robust at all levels. The benefits are huge: faster feedback during development, fewer bugs in production, better designed code, and a less fear during refactoring. Unit tests also serve as documentation. When someone new joins your project, reading the test can help them understand how the system is supposed to behave. But remember, no testing strategy is complete without integration and end-to-end tests. Think of unit testing as your first line of defense. So benefits of unit testing can be detect bugs in early development cycle, encourage modular, loosely coupled code, improving developer confidence during refactoring, and serve as documentation for expected behavior. However, the limitations are unit tests do not catch integration bugs. They must be combined with other testing levels, and it can give false sense of security if poorly written. As mentioned before, with Python you can use PyTest. With JavaScript, you can use Jest. With C# you can use NUnit or XUnit. JUnit assertion. So what is assertion? Assertion are the foundation of JUnit tests. They help verify the result of a method that we expect. For example, in a code we would simply write assert equals and then put in parentheses for calculator.add parentheses 2, 2, and this would check 2 plus 2 equals 4. Other assertions include assert true, assert false, and assert throws. These methods are a part of the org.junit.jupyter.api assertions, which you can look up online, and are usually imported statistically for a clear syntax. Proper use of the assertions leads to precise, reliable, and meaningful tests. Assertions are critical because they tell you exactly what behaviors you're verifying. If an assertion fails, you immediately know what went wrong and where it went wrong. It's also good to practice to add a message to your assertions. So it's good to practice these small things. Why use assertions? They make your test self-validating. They provide immediate feedback if something breaks. They encourage clear thinking about what each piece of code is supposed to do. Now, what are assumptions? Assumptions are used when you want to run a test only under a certain amount of conditions. For example, assume true. Assumptions live in the same area which I mentioned before, org.junit.jupyter.api assumptions. Again, you can find that online. Assumptions class and can help you avoid false positives. They're especially useful in multi-environment CI steps where some tests don't apply to all stages. JUnit provides methods like assume true, assume false, and assuming that to express these conditions. If the assumption is not met, the test is skipped rather than failed. This helps keep your test reports clean and meaningful, especially when you're running hundreds or thousands of tests in different environments. Assumptions are a great way to build smarter test suites that adapt to their context. So, assumptions define preconditions for running a test. If the assumption fails, the test is aborted, not failed. Used to skip irrelevant tests, depending on the runtime conditions. Assertion still determine test outcome if assumptions are met. An assumption being true does not guarantee test success. It just means that the test will run, and assertions must still pass for the test to succeed. Now, what was Martin Fuller's logic? The way Martin Fuller describes his unit testing is his perspective on it, is it emphasizes flexibility. There is no single strict definition of a unit. Some teams treat a class as a unit. Others include tightly coupled collaborators. He introduces two styles, solitary with mocks and sociables with real collaborators. Martin Fowler leans towards sociable tests for simplicity, but acknowledges solitary tests are vital in certain scenarios. His writing reinforces that the primary value of unit testing is to promote fast feedback and better design. Solitary tests uses mocks or stubs. Sociable tests lead to unit interact with real collaborators. Each approach has pros and cons. Solitary tests are faster, more reliable, but may require complex mocking. Sociable tests are easier to write, but may introduce external dependencies. So it really depends on what you're testing and what you want to use while you're testing. Some common elements of unit testing should be low level, which is tests are small, isolated pieces of code, should be fast, should execute in milliseconds to support continuous feedback, and should be developer written, which is most unit tests are written by programmers themselves using tools like JUnit. Solitary tests prevents failures and are required more setup. Sociable tests are faster to write and often sufficient unless dependencies are unstable or remote. Mock objects. Now, what are mock objects? Mock objects simulate dependencies so you can test in isolation. For example, instead of calling a real payment API, you can mock it to return predefined responses. Mockito is a very popular Java library for creating mocks. Mocks help make tests faster, more reliable, and less dependent on external systems. They are especially useful when testing errors and handling interactions. Mocking is essentially for testing behavior, especially when you want to check if an object interacted with another system correctly. For example, you might want to mock a database to confirm that a save method was only called once. Using mocking frameworks like Mockito, you can verify interactions, set return values, and simulate exceptions, all without touching the real system. So basically a form of isolation, and in the diagram, as we can see here, without mock, it's a much longer process. You would go through tests. From tests, you would go through a test scope, which is service A, service B, service C, service D. Then you would go to service E. With the mock, it's much simpler and causes more isolation. It would be straightforward, which is tests, straightforward to test scope service A, and then straightforward to mock server. And you can use tools like Mockito, EasyMock, or JMock. As for speaking about mocks, mocks are not stubs. They are two completely different things. So mocks and stubs, basically how Martin Fowler defines 5 types of test doubles. It's dummy, fake, stub, spy, and mock. Mocks are used to verify behavior, and some of the questions that are asked are, did a method get called? What are the arguments? Stubs simply returns predefined responses. Understanding this distinction is crucial in deciding whether you're validating output or behavior. Using mocks properly supports interaction-based testing, while stubs are ideal for simplifying test setups. So a dummy is unused parameter placeholder, stub is provide pre-programmed responses, fake is working implementation not suitable for the production, mock verifies interactions and accepted calls. Spy is captures methods call data for later assertions. Now the differences, mock versus stubs, as shown here on the chart, it's supplies data to tests, passive, return test data for stubs, and then mocks, as we said, verifies the behavior of the system, active, and ensures a method was called at least 3 times. What is test-driven development? Test-driven development is a process where you write tests before writing the implementation. Here in the diagram, we can see that the cycle is red, which is writing a failure test, green, writing code to pass it, and refactor, clean up the code. Like a cycle. Test-driven development improves design, ensures test coverage, and helps avoid over-engineering. It forces developers to focus on what the code should do before thinking about how to implement it. Tests that practice test-driven development often report fewer bugs and more maintainable code bases and are more reliable. This cycle, red, green, refactor, promotes better design, leads to more modular, maintainable code, and it acts as a form of specification. Your test defines the expected behavior, and your code fulfills it. This ensures alignment between business requirements and implementation from the start. So, it does improve software design by forcing decoupled test units. Okay, now what makes a good unit test? So Eric Elliott gave at least 5 key questions, which is what is being tested, what should it do, what is the setup, and what is the actual result, what is the expected result. Good tests are descriptive, specific, and have a clear intent. They also act as a documentation for future developers, showing exactly what behavior is expected in a specific scenario. Tests should be descriptive, focused on one behavior, and easy to understand. Not just for you, but for your entire team. You should avoid ambiguous names like test 1 or check method. Instead, use names like should return false when user is active or inactive. A good test not only verifies behavior, but also helps future developers understand the system and what it's supposed to do. And it also reduces false positive, negative, and improves debugging. Now, qualities of good tests. Kenneth True outlines characteristics of effective unit tests. They should be deterministic, simple, isolated, maintainable, and readable. He encourages using the AA method, or the AA pattern, which is arrange, act, assert. You should avoid logic like if-else statements, if statements, and loops. Tests must also run quickly and independently to be reliable during development and continuous integration. Isolation means the test does not rely on external systems. If your test connects to a real database or file systems, it's no longer isolated and may be flaky. Readability is key. Your test should be easy to read as your production code. So anti-patterns to avoid is using if statements or loops, relying on global variables or mutable shared state, tests that fail immediately. As for unit versus function and integration testing, here in the pyramid we see there's function testing, integration testing, and unit testing. Now, testing comes in layers. Unit testing validates individual pieces of code. Integration tests check interactions between modules. Functional tests validate business logic and workflows from the user's perspective. SitePoint recommends a test pyramid, more unit tests, fewer integration tests, and even fewer end-to-end tests. This approach ensures wide coverage while maintaining fast feedback cycles. A good practice is to follow the testing pyramid, lots of unit tests, fewer integration tests, and mainly end-to-end tests. Unit tests give us fast feedback, integration tests catch communication errors, Functional tests confirm that your application works well in the real-world conditions. All three important things, but each serve as a different purpose. Now, JUnit 5. JUnit 5 is a complete rewrite that brings an architecture of modern Java features. It has three components: Platform for discovery and execution, Jupyter, new APIs, and Vintage backward compatibility with JUnit 3.4. It supports dynamic and parameterized tests, better lifecycle control, and better IDE integration. These improvements make it easier to write clean, scalable tests. Jupyter is the main API for writing tests, while Vintage allows older JUnit 3 and 4 tests to run alongside new ones. So it's flexible, simple, modern, Java friendly, and it's a good AI tool. And it builds foundation, and it helps the CI and CD pipeline compatibility. Now, JUnit 5 annotations. These annotations you can use in code, such as @test. It marks the method as a test case. @before each runs before each test, setups tasks. @after each runs after each test, and it cleans up the task. With these methods, it helps make our code more cleaner, more precise, and more reliable, and it allows us to understand the code and have other readers understand our code. So this is just one of the examples that you would use in a code. You would write the code, class calculator tests, calculator, then you would write your annotations, @before each. You would continue your code, void setup, calculator equals new calculator. Continue again, but then this time you would also use @test, @display names. Continue your code, and then at the end of your code you would write @after each. So mainly these annotations help us clear up the code, understand what we're writing, and continue on from there. @test, it allows us to group relatable tests, and @display names improves testability reading in reports. @after each allows us to regroup related tests. Now, what is software testing? Software testing ensures software behaviors as expected and meets all the user's needs. It includes statistics, testing like code reviews, and dynamic testing like unit and system tests. Tests can be manual or automated. The goal is to reduce bugs, improve quality, and build confidence in the software. Testing is an ongoing process and not a one-time activity. Testing isn't a phase that can happen after coding. It's continuous. It has a process, and it should occur throughout the development of the code. It helps ensures quality, reduce costs, and build a user trust. So here we can see in the diagram that there's different testing types: unit testing, integration testing, and system testing, and acceptance testing. Now, what are these, and what are their main focus and their goal? Well, while we're coding, we always have one goal: to make sure that the code works. So unit testing focuses on individual components, and the main goal is verify small units of behavior. Integration testing focuses on the interactions between the components. The goal is to ensure modules work together correctly. System testing focuses on the entire application, and the goal is to validate the end-to-end functionality. Acceptance testing, the focus is requirements from the user's perspective and confirms readiness for the release. So it's a step-by-step process, but that's how code works. Everything is a step-by-step process. Categories of testing is static testing. This is without executing the code, so this could be reviews, analyzing tools. Then there's dynamic testing, which involves running the software and observing outputs. And then there's manual testing performed by human testers. Then there's automated testing performed by using tools. So we always need tools, we always need a step-by-step process, and we always need to make sure that our code is understandable, easy to read, and flexible, and not only just for us, but for other people as well. Software testability. So what is software testability? Testability is how easy it is to test a system. Highly testable code is easier to understand, and it has clear inputs and outputs. It is free from side effects. Principles like observability and controllability play key roles. Practices like dependencies, injection, separation of concerns, and clean architecture improves testabilities. Better testability leads to a higher quality and faster feedback. So the better your code is, the faster your feedback will be, and the easier it is to improve and understand it. Code with poor testability is hard to verify and often relies on a global state and has hidden dependencies. Improving testability usually leads to better design, fewer bugs, and faster development cycles. So now, some of these things would be fewer bugs escape production, tests are easier to write, run, and maintain. Testability defines how easily a system can be tested. Key traits: observability, controllability, simplicity, stability, and understandability. And these are really great key traits to have in your code, because once you have that in your code, it is set and the program will be working. Improved by modular designs, by logging, and dependency injection. High testability leads to faster issue resolution and stronger unit tests, crucial for building a robust, maintained software. To wrap up, unit testing is essential for building high-quality software. Start testing early, using the test-driven development when possible. Write a clear, focused, and isolated test using tools like JUnit, Mockito. If you're doing Python, you can use PyTest. Don't rely solely on unit testing, because there are different types of testing, as we've mentioned. You can use integration or system tests too. And most importantly, make testing part of your development culture, not just a checkbox. So when you're doing your code, have a process plan. As you can see in this diagram here, you want to design test cases, go from there, test the case, then you would want to prepare the test data, test the test data, then you would want to run the program with the test data, test the results, compare results to the test cases, and then test the reports. It's all a process. And don't test everything, test what matters the most, and always complement unit tests with other testing types. When testing is a part of your development culture, it leads to a better outcome for developers, teams, and users. And this will be good for your future work life too. So, in summary, it's recommended to use multiple types of tests. JUnit is good, unit testing is good, but so are other types of tests, depending on what your code is and what your situation is. User unit tests to guide design test-driven development, keep tests isolated, fast, and readable, adopt mocking where needed but avoid overuse, combine unit tests with integration and scenario tests for full coverage, run tests frequently using CI pipelines. Thank you so much for watching my presentation on unit testing in software engineering. I hope this gave you a valuable insight into the theory and practice of unit testing. And if you're new to testing, I encourage you to try it for your next project. Even writing 1 or 2 small tests can make a big difference, and practice makes perfect.